Now we're going to do some important calculations for unit conversions between these parameters basically. First I would like to start with a note on the unit of mu0, permeability of free space. So if I do a unit analysis on mu0, first I can start with Faraday's law. Now Faraday's law says that the electromotive force epsilon is equal to minus inductance di dt, the derivative of current with respect to time, or minus n, a number of turns d phi flux derivative with respect to time d phi dt. So this is Faraday's law. And you can see that the flux L times I is n times phi, the number of turns times phi. So the flux is Li over n, which is equal to, in SI units, mu0 times h times the area A. So you can find that mu0 can be written as Li divided by number of turns n, magnetic field H times A. So this gives us, for the unit of mu0, the following. So mu0 is the unit of inductance Henry, unit of current amperes, divided by the number of turns doesn't have a unit. We have the magnetic field H, which is measured in amps per meter, and the area in meter square. So this gives us, as a result, Henry, because the amps disappear, meter disappears, we have Henry per meter. So the SI unit for permeability of free space, mu0, can be written as Henry per meter. So that's one way to do it. Now, a second approach, if you look at the flux, which is mu0 times h times A, mu0 is the flux divided by magnetic field times the area A. So this tells us that mu0 has the unit of flux Webers divided by SI unit of magnetic field ampere per meter times meter square. Again, one of the meters disappear. So I find that the unit of permeability of free space can be written as Webers divided by ampere meter. So that is following the flux, magnetic flux. Now there's a third way. I can look at the force acting on a current carrying wire in a magnetic field. So that comes from the Lorentz force, and it is mu0 I, the current it carries, times the length vector L cross with H, which is a vector that points in the direction of current, and magnitude is the length. So you can see from this equation that mu0 can be written as the force divided by I L cross H. So from the units point of view, mu0 is newtons divided by meter is ampere is the current, meter is the length, ampere per meter is the magnetic field. So we have meters cancelling here, which gives us Newton divided by ampere square. So we find that mu0 can be written in units of newtons per ampere square also. That is the force approach. Okay, so finally, let's put a remark here. You can see all of this analysis is in SI. Note that we don't have a mu0 in CGS EMU system. In the CGS EMU picture, mu0 is 1 and dimensionless. So we cannot do a similar analysis for mu0 in CGS EMU. So that's for mu0. Now let's talk about the pole strength, the unit of pole strength. I'm going to approach this from SI point of view first. Now we have the equation between two poles written in SI units, mu0 over 4 pi P1 P2 divided by r squared. So this is from the torsion balance experiment, remember. And you can see that the pole strength squared, P1 P2, is the force 4 pi r squared divided by mu0. So the pole strength unit then will be square root of Newton meter squared divided by Newton divided by ampere squared, because we have shown that I can write mu0's unit is Newton divided by ampere squared. So the Newtons cancel, I get the ampere squared upstairs, so the pole strength becomes ampere meter. So in SI the pole strength is given in ampere per ampere times meter. So this is our SI unit. Now in order to convert to CGS, let's give some values. Now let's assume that I have a pole strength of 1 ampere meter. The distance between the poles is 1 meter, and we have the mu0 value, which is 4 pi 10 to minus 7 newtons divided by ampere squared. So if you calculate the force between these two poles now, you will get 4 pi 10 to minus 7 Newton divided by ampere squared divided by 4 pi. The pole strength squared, 1 divided by 1 meter squared. So the answer is 10 to minus 7 newtons. And remember, if you want to convert newtons to the CGS unit, the conversion is as follows. 1 newton is 10 to 5 dynes of force. So now I go to the CGS picture. In the CGS picture, I can write the force between two poles as P1 P2 divided by r squared, and that means P1 P2 is Fr squared. So the unit of the pole strength will be then square root of dyne centimeter squared, which we define to be unit pole strength. So in CGS EMU units, the pole strength is unit pole strength, which is dyne to the 1/2 centimeters. Okay, So now in the previous example here I had a force of 10 to minus 7 newtons. So a force of 10 to minus 7 newtons is 10 to minus 2 dynes. And I had a distance between the poles r 1 meter, which is 100 centimeter. So I would like to find how many unit pole strengths I have here. So 10 to minus 2 dynes of force is p squared divided by r squared, which is 100 centimeter squared. So that gives me for pole strength squared 10 to 4, 10 to minus 2, 100. So I find that the pole strength is 10 unit pole strengths. Therefore, I have the following conclusion for conversion between CGS EMU and SI units. 1 ampere meter of pole strength is equivalent to 10 unit pole strengths in CGS EMU units. Okay, now let's move on to magnetic field. So let's talk about unit of magnetic field H. Let's start with the SI picture again. The magnetic field is defined as pole strength P divided by 4 pi r squared. This is in SI units. Now that means the unit of the magnetic field should be, because the unit of pole strength is ampere meter and we have r squared there, which is in meter squared, so that should be ampere per meter. So the unit of magnetic field in SI, H, is ampere per meter, and the force between the when you put a pole in a magnetic field, H is mu 0 P H. So if I give some numbers here, if the pole strength is 1 ampere meter, and the radial distance is 1 meter, the magnetic field it creates will be then 1 over 4 pi amps per meter. So let's move to the CGS EMU picture. In CGS EMU, the magnetic field is given as the pole strength divided by R squared. So this is in CGS electromagnetic units. And the magnetic field has a unit pole strength divided by centimeter squared, which we call Ørsted. Okay, so now I go back to this example. If I have a pole strength of 1 ampere meter, remember we found that 1 ampere meter is 10 unit pole strengths, so that is 10 unit pole strengths, and the distance is 1 meter, which is 100 centimeter. Then the magnetic field should be P, which is 10 unit pole strengths, divided by 100 centimeter squared. That is 1 over 1000 Ørsted. Okay, so we have the magnetic field 1 over 4 pi amps per meter must be equal to 1 over 1000 Ørsted. Therefore, we find that 1 Ørsted is 1000 divided by 4 pi ampere per meter, which is roughly 79.6 ampere per meter. So this is how I convert the magnetic field between SI and CGS EMU units. And finally, I would like to take a look at magnetization. So let's talk about unit of magnetization. Now, magnetic moment is current times the area for a current loop in SI units, and this has a unit, therefore ampere meter squared. Now there is something called magnetization. Magnetization is the magnetic moment per volume, that's defined as capital M is magnetic moment per volume V. So it has a unit, therefore the magnetic moment is ampere meter squared divided by meter cube, which is ampere per meter. So SI unit of magnetization is ampere per meter. Now I would like to go to CGS EMU picture. The magnetic moment is defined as pole strength times L, the distance between two identical moments in the CGS EMU picture. And therefore it is measured in a unit pole strength times centimeter, which is called electromagnetic unit EMU. So magnetic moment is measured in units of EMU. Now 1 EMU is 1 unit pole strength centimeter, and 1 unit pole strength is 10 to minus 1 ampere meter. So this is 10 to minus 1 ampere meter. 1 centimeter is 10 to minus 2 meter. So therefore 1 EMU is 10 to minus 3 ampere meter squared, or we can say that 1000 EMU is 1 ampere meter squared. So that's how the magnetic moment converts between CGS EMU and SI units. Now if I go to magnetization, magnetization is magnetic moment per volume. So if you have a magnetization of 1 EMU per centimeter cube, so you can see that here. So let's first do this calculation. The unit of magnetization will be magnetic moment, which is measured in EMU, and the volume is measured in centimeter cube, so it will be measured in EMU per centimeter cube. So if you have 1 EMU per centimeter cube, that means 1 EMU is 10 to minus 3 ampere meter squared, and 1 centimeter cube is 10 to minus 6 meter cube. So that means you have 1000 ampere per meter. So the conversion between CGS and SI for magnetization is 1 electromagnetic unit per centimeter cube is 1000 ampere per meter of magnetization. This basically covers the widely used quantities and units in the CGS EMU system. So we have the conversion between magnetization, magnetic field, unit pole strength, and mu zero between these systems. So once again, I can figure out unit of mu zero using Faraday's law, which gives me Henry per meter, flux, Weber per ampere meter, or the force on a current carrying wire in a magnetic field, newtons per ampere square. In CGS EMU, mu zero is 1 and dimensionless. If I consider unit pole strength, the torsion balance experiment gives me mu 0 over 4 pi P1 P2 over R squared for the force, which gives a unit of ampere meter for pole strength. And if I assume that I have a pole strength of 1 ampere meter, distance between poles 1 meter, identical poles, and mu 0 is 4 pi 10 to minus 7 newtons per ampere squared, the force should be 10 to minus 7 newtons, because 1 newton is 10 to 5 dynes, that is 10 to minus 2 dynes in CGS units. The force between two poles in CGS is P1 P2 over R squared, so the P pole strength is measured in unit pole strengths, which is square root of dyne times centimeter. 10 to minus 2 newtons of force is pole strength squared divided by 100 centimeters squared. That gives us a pole strength of 10 UPS, and that means my pole strength of 1 ampere meter is equivalent to 10 unit pole strengths in the CGS EMU picture. Magnetic field in SI is P over 4 pi R squared, and since P is measured in ampere meter, the magnetic field strength is measured in ampere per meter, and so that the force between two poles is force on a pole in a magnetic field H is mu 0 pH. If I have a pole strength of 1 ampere meter at a distance 1 meter from this pole strength, I have a magnetic field 1 over 4 pi ampere per meter. The magnetic field in CGS is P over R squared, which is in unit pole strength per centimeter squared. That's called Ørsted, 1 Ørsted. So if you have a pole strength of 1 ampere meter, which is 10 unit pole strengths, a distance of 1 meter, which is 100 centimeters, we find that the magnetic field should be 1 milli Ørsted. So 1 milli Ørsted is 1 over 4 pi ampere per meter, therefore 1 Ørsted is 1000 over 4 pi, or 79.6 ampere per meter. The magnetic moment is current times area in SI for a current loop that carries a current I has area A. It's measured in ampere meter squared, and magnetization is magnetic moment per volume. It is measured in ampere per meter. Magnetic moment in CGS is pole strength times the distance between the two identical poles, P times L. It is in UPS centimeter, which is EMU, called electromagnetic unit. And 1 unit pole strength is 10 to minus 1 ampere meter. So if we go back here, 1 unit pole strength is 10 to minus 1 ampere meter. And 1 centimeter is 10 to minus 2 meter. 10 to minus 3 ampere meter square, or 1 ampere meter square is 1000 EMU. If you go to magnetization, that would be EMU per centimeter cube, and 1 EMU per centimeter cube is because 1 EMU is 10 to minus 3 ampere meter square and 1 centimeter is 10 to minus 2 meters. The ratio becomes 1000 ampere per meter. So to go from SI magnetization to CGS magnetization, we have to multiply it by 1000. 1000 ampere per meter is 1 EMU per centimeter cube.